much. Yes, although it appears to be a sole author, I think you will notice the shadow or ghost of my colleague Michael Heather in one or two places. So, we will see. Right, so outlining the presentation, I'm going to look at two recent aspects, the Topos and the Monad. And that's what we think, that these two features together can do a lot of what we want from category theory for our universal information systems. Well, last August, we talked quite a lot about the Topos, so I'm going to start off with the Topos just to refresh your minds with what that is. But basically, we're going to apply the Monad to a Topos in this talk, and we're going to review it a bit. There'll be some discussion. So that's the basic idea. Oh, I've already pressed the wrong one. Right, next. Yeah. So what's the Topos? Well, Topos is, I don't like to purely call it a structure now, because a structure indicates to me something which doesn't have any activity. It's just something that you hang things on. I think it's more like a structural data type, where you could have lots of processes designed for part of the Topos, has its own internal logic, for instance. So it is a framework, if you like, but it does have a lot of process and activity within it internally. So I prefer to call it a structural data type now, rather than just a structure. It's based on the Cartesian closed category, which appears to be the basis of most things that are useful in category theory. First thing that Cartesian closed category has is products, so A times B. Once you have a product between two objects or categories, you have the possibility for relationships, because a relationship is a subset of the product. So without products, you can't really deal with relationships. Cartesian closed category has closure at the top, has a terminal object, so everything maps onto this terminal object in the closure, not necessarily an initial object, there's always a terminal object to close at the top. And the great thing about that, of course, is that you can then reverse all the arrows, and your terminal object can be used for addressing everything in the Topos. So you have some gain from that, but it's closed at the top, not necessarily at the bottom. Connectivity comes through exponentials, like B to the A, all the arrows from A to B. We'll be dealing with that a little bit later, but that's the lambda calculus, if you're familiar with that, where if you have
so you call existence of exponentials connectivity?
Have we proved it?
Well, I don't know what connectivity means in category.
Okay, what
I know what it means in topology, but you also
I'm equating it to exponentials here, I would say.
So connectivity means A to B is different.
Yes, so A to B would be all the arrows from B to A, and it comes about in currying when you are taking a function with multiple arguments and you're converting it to a function with one argument.
You call the existence of such things complicated.
Yeah, yes, Mike and I do. I think I should stress you won't find that in the books so much, but we think of it as that, because it is all the arrows.
Yeah, I'm mostly ignorant of category terminology, but connectivity, of course, means something in topology, so I have to accept it.
Yes, that's a very good point to make. That is rather our own language, I would say. Yeah. Internal logic, that can be Boolean or the intuitionistic. That is a language within a Cartesian closed category. That's why I'm going for this term more like data type, because data types in computing have quite a lot of functionality within them, as well as the structure, particularly in languages like Java, for instance. So we do have the internal logic. We have identity, which comes from this closure at the top. You can turn all the arrows round, and then the terminal object acts as an identifier for a handle for the whole of the category. So every Cartesian closed category can be addressed through an identifier, identity function. is what it's called. So that's important. And also, this is another thing that perhaps Mike and I have developed, interchangeability of levels. You can do things at the object level, you can do things at the category level, and nobody seems to worry too much. But we introduce a bit more flexibility there. So that gives you your Cartesian closed category, which is really the basis of most useful, in quotes, categories in the universe. Now we add three things to that. So we add the sub-object classifier, and that is rather like a search on a topos to produce a sub-topos. So you're actually applying some search logic, and you are deriving what I'll call a sub-topos out of it. You've also got the internal logic of heighting, which is intuitionistic. That's if you make the sub-object classifier more general, you can go to the heighting logic. And then we have what I call the reflective sub-topos for query closure. If you do a query on anything, it's very important to know what the output type is. Otherwise, you're left with something printed on a page or in an anonymous file in your computer system. You really want to know what the type is, and that is potentially achieved through the topos. So we get a topos, and I think just give an overview of what we've been doing over the past 2 years. It takes quite a while, category theory. You sort of do a chapter of McLean or something like that. It takes you quite a while to absorb. So the sort of things this was put up last year, but I've changed queries to queries within a topos, because today we're going to look more at functionality external to a topos, how you actually process a topos itself. And there we have the use of sub-object classifier, particularly par objects. Examples of heighting intuitionistic logic. And this is the thing that we're really adding today, is applying process to a topos. So this is actually taking the whole of a topos and running a process on it, which will be a monad. Database design, we've experimented with these over the last couple of years. Co-Cartesian approach, pasting of pullbacks, recursive pullbacks, and allegories. But I'm not going to do allegories again, so you can rest assured on that. And the sort of progress we've made, the red is what I've added since last year. That was just to clarify that by queries there, I mean queries within a topos, not queries outside of topos. The heighting examples stalled for a while. I'm happy to say that we've got our work going again at Northumbria University, where there's somebody who did his MSc with Goldblatt. I don't know if you know Goldblatt was a famous category theory person from New Zealand. And so we're hoping to get some examples there of the heighting. External process on a topos is added, that's today's topic, monads. Looking at the list down there, we're going to start off looking at this a bit, this co-Cartesian. That was thought to be a way to handle normalization. Now, normalization is a database technique which is used to check whether your relations are in optimal form. And it is, I think it's the ultimate categorification, really, in that when you try to translate that into category theory. By that I mean you're taking a concept outside of category theory and you're trying to put it into category theory just by a simple translation, without going back to basics and saying, how would I really achieve this in category theory if I was completely ignorant of how the subject's done at the moment. So we think some of these things are categorification. But in fact, this pasting of pullbacks we're going to see, the 5NF definition, fifth normal form, actually does correspond to what I'm going to say about pullbacks.
What's 5NF?
Fifth normal form, it's a project join, which says that if you project out relations, you can always join them back to recover the original. And if there's any loss in that process or ambiguity, it means your relations aren't identified properly, aren't defined properly. So that was the ultimate of date and cod and people like that. So So the addition of the monad is the important thing. Yeah, so I think we'll go and look at a Cartesian closed category. This is a pullback. Now, I think we use pullbacks, probably some people would say far too much, but we find they do everything really. So a pullback is, we have the two objects here, and pullback is of S times M over R. So it's the two objects there, S and M, standing for student and module. So that is the relationship between student and module in the context of result. So it means that is a result. They could have other relationships like lecture attendance and things like that. But that's the idea. And that relationship is represented there, S times M, in the context of R. So that's a pullback, and that I think is the most useful construction in category theory from the structuring perspective. You note we've also got this logic in here, so we've got some of this standard predicate logic in here. We have there exists, that's the existential operator, we have the for all there, and there we have delta, which is a diagonal, which is comes in between the there exists and the for all. So we have this logic in the pullback, which can be intuitionistic. And you see also we have projections onto S, projections onto M, and then these are inclusions here. So that's a very important structure, but for a while we've relied on this single diagram for quite a while, and I thought people might say, well, what happens if your database contains three relations? How do you actually put them together? And Mike and I had quite a long, shall we say, debate on this, which probably went on for about 3 or 4 years, where it's, Mike didn't like the idea of pasting, and I thought it was the best thing to do. So anyway, we've gone in for pasting in the end.
So could you remind me, so the del, the
diagonal
it sounds diagonal.
Yeah, there's an adjointness there, which I'm going to come to.
Okay.
There exists is left adjoint to delta. Delta is right adjoint to there exists. Delta is left adjoint to for all, and for all is right adjoint to delta. So yes, there's adjointness there.
Okay.
Yeah, good. So what happens if you start pasting these pullbacks together? Well, what we've got here is we've got more relationships, and we have this bottom square here is what we had before. That's exactly the same logic as before, but I've now added a relationship between departments and modules. Departments offer modules, and universities include departments. And you'll note that these pullbacks, the structure is actually getting more complicated. And so the pi L there is S, and the pi R is M. But the next level up, we go to S times Rm, which is that one. That is the left project of that product, and the right project goes over there, which is called pi R prime. So the structure looks a lot. Obviously, I could simplify these extensive products. But you can see the principle that I've just pasted on to that original pullback, 2 more pullbacks, P2 and P3. I stress that those labels, they're just labels for the purpose of this talk. P1, P2 and P3 have no significance in category theory. So, can we test these? And you can. A pasted pullback is only a valid pullback if all inner and outer diagrams are pullbacks. So if you've got any diagram there that is not a valid pullback, or a combination of two, the thing fails. I will show you an example of that in a sec. So I've got times 6. What's the number 6 doing there? Well, we have 6 pullbacks there. We have P3, P2, P1, and then we have P3 plus P2, P2 plus P1, and P3 plus P2 plus P1. So we have 6 pullbacks in that diagram, and every one of those has to be a valid pullback, not a valid category. It has to be a valid pullback. for the pasted pullback to have that type. That's the basic idea. So you can put in the same logic arrows, the exists and the diagonal and the for all across there. I've just missed out some of the inner structure. So you could treat it as a single pullback with those logic arrows going across there. So that's the same diagram as we had before, but it's just a single pullback. So what's happening here? Well, here I've decided to add lecturers. You've probably noticed that lecturers were missing from this university. Make some comments about that. But sorry. So what I've done here, is lecturers can be in more than one department. So that means the relationship between department and lecturer is not hierarchical, it is many to many. And so what I've done to try and introduce this is to shove this extra pullback onto that diagram there. So we've added lecturers, and that's a valid pullback square, D times ML to M. P4 is a valid pullback, but the whole structure is not. Because whilst there are valid pullbacks here, this square here, including P2 and P4, would have to be a valid pullback for the whole structure to be a pullback. And P2 and P4 does not have the required structure for a pullback. You can't. So,
can you explain that?
Well, for a pullback you would expect, if you put this as a square, you would expect it to be something like D times ML. Well, it gets quite complicated, doesn't it? There's nothing up on this left-hand side which is going to make a nice entry to define the product. So you see the pullback structure is product, and then you have the two things that you've involved in the product. That's U, and that's S times RM times MD. That's that one there. So if this were to be a pullback, I don't see how you could make it a valid pullback if you wanted to include those two squares. You can try if you like, but I don't think it will conform to this pattern of the projections. And fifth normal form would also fail that for those who like fifth normal form, because that's not a valid construction. So that's not a valid pullback, so we do have our limits. And one way around this is to introduce D times L. So we go from D down to D times L and M, and then the whole structure can be made into a fully pasted pullback. So we can handle many-to-manys, but we have to introduce products on this right-hand side. So how many pullbacks are there? Well, there's probably a better way of counting them than I've got. You've got 4 at the basic ones. You've got 3 where you could take them in pairs, that's 7. You've got 2 where you take them in threes, and you've got 1 with a whole lot. So 10. So every one of those inner and outer pullbacks has to be a pullback for it to be a pasted pullback. So it's always useful to explore these things. So we think we can now handle large applications with this. The other thing that we were working on is the sub-object classifier. That's to finish the Topos example. This is a Boolean example. So those are the possible values. That's the sub-object classifier, 0 and 1. That's the Topos. That's the object you're searching on. And this is like your SQL or database query, IJ. And the idea is that you pick out from the Topos those sub-objects which satisfy this search statement to satisfy this sub-object classifier of 1. That would be 0 if they're false. So that's really how you would represent an SQL statement in category theory. The problem is, this is, I would say, should be your sub-topos, because that really is 1 topos times S in the context of your sub-object classifier. But there are some problems with that, and Mike has raised some quite serious objections to how you play around with this. Basically because it's not clear whether this is the intention or the extension, what you're dealing with. And that really comes through the whole of my talk today, that pure mathematicians are very good at glossing over intention and extension. Intention being the definition and the extension being the data values. And we have done a lot of work on this, but we haven't actually connected it through to this approach. So I will put that as a qualification. So what the pure mathematicians do, I think they're really quite sharp in this, is they don't argue about the whole square, they draw the square, and then they just argue about that arrow and that arrow in isolation. So they detach them from the diagram. And so we do have some trouble with some of the undecidability, if you like, as regards intention extension. So I will. So have we finished the? Yeah. So that's really the Topos. So you can see it's quite a capable thing. You can build up these pasted pullbacks, you can query it, and all sorts of things. Now let's look at external process. Well, I'll start off with metaphysics, of course, for this, and Whitehead, process and reality, which we're very interested in. In the information systems world, this comes down to a transaction, typically. You can imagine these in the universe as well. And transaction is a unit of activity on a system which changes the state from, so it could be that you're paying me £20 in a bank account. Obviously that is changing the states of our bank accounts. It can be very complex, this transaction processing. Can be hundreds of instructions, but generally the whole is viewed as atomic. So as a binary outcome, it's the whole thing succeeds or the whole thing fails. So if you find just one problem out of 100, you go back to the beginning and send a message to the user saying it's failed and takes it back to the starting point. And of course this is why the before and after states must be consistent in terms of the rules. So they're complex rules often governing these things. Intermediate results are not revealed to others. That's very important when you think of it, because if I was paying you some money and I didn't really have the money in my account, but I contrived to have a transaction which took a long time to run and had improved my bank balance, but it wasn't sustainable by the end of the transaction, that would obviously distort things. And the other important thing is the results must persist after the end. So when you finish, the results have to last for as long as is necessary for the application, which could be years or it could be months. So that's a rather informal view. Getting a bit more formal, we have the principles of ACID: atomicity, consistency, isolation, durability. And it's a logical technique for controlling the physical world. A lot of these systems that do this go back to the 1970s, even the 1960s, like TICS is one of them, used in IBM. And get a bit more technical, we think it requires 3 cycles of adjointness between the initial and target state, which I'm going to show on the next slide, I think. First you mock up your change, this is what we plan to do. In the second cycle you review the changes against all the rules, and in the third cycle you do the housekeeping to mop up after it, either storing the result on a disk or sending it over a network. It has to be said, this durability is so important now. Lots of oil companies, say something like that, with headquarters all over the world, they will send important transaction results over the network to different countries. So if you blow up their headquarters somewhere, they won't collapse the company. So that's ACID is an important principle in real life. So in the earlier work, I think it was ANPA 2010, it was at Cambridge, we used adjointness to represent a transaction, employing multiple cycles to capture ACID. And now we're going to abstract this work into a monad. That's the basic idea. if you're familiar with a monoid, people familiar with a monoid? I don't know. No. It doesn't help, as Mike says. It's a set theoretic concept, so you're best without it. Okay, but basically a monoid is where you have two elements. You have m times m to m multiplication, and you have an identity 1 to m on the multiplication. So a monoid has been around for a long time as rather like groups. It's similar to that sort of thing. It's an extension to set theory. But I'm not going to deal with monoids anymore. Right, so let's get on to adjointness now. And what we had in the 2010 paper, which we did write up, by the way, is we have these 3 cycles, GF, GF, GF. Now we've got 2 categories here, L and R, for left and right. So that thing up there means we go over F, G, F, G, F, G. So we do 3 cycles around the structure. And we're assessing all the time the unit eta in L and the co-unit epsilon in R. Eta is the unit of adjunction. Important to realise with categories that when you do that, you go over there to an object in R, and then you come back with G to an L. Is your object the same? In other words, is G, F, L, the one you come back with, the same as the one you started with? And if you were doing a transaction on a bank, for instance, you would assume it wouldn't be when it came back, because it would have added some information for you to test. There'd be a difference. And so eta indicates there's been a difference as the unit of adjunction. And it's the same over this side with the co-unit epsilon. So we have these 2 adjointness techniques. And adjointness is specified by the functor F, the functor G, that unit there and the co-unit there. That's the basic idea. And F is left adjoint to G, G is right adjoint to F. So that shows what eta is. It's the identity of L at the starting L and mapping it, comparing it with GFL. That's the basic idea. Now, another thing which comes from Whitehead, I think, is that these cycles, although it looks like you go around a cycle like a for loop in a computing program, we don't really think it is that. We think it's all performed simultaneously. It just snaps on the solution to the adjointness, and I think that's what Whitehead calls prehension in his book. Is it process reality? Yes, meaning grasp. So the system grasps at a solution. It doesn't, not like some of these computer programs. So what are we going to do to handle this? Well, this 3 cycles of adjointness is really a bit low level. And the promising technique, we think, is the monad. We did think this in 2010, but we were really too busy absorbing the earlier work. We did write up some of the monad stuff in a paper at the Edge. And so what's a monad? It's used in pure mathematics for representing process, and it has 3 cycles. You note I'm putting cycles in quotes. That's because I don't like to think of it as being just boring cycles. It's more a snap of iteration to give consistency. Now, the monad's not just a pure mathematics concept, it's also used in functional programming. And this formulate the process in an abstract data type. So Haskell, which seems to be the best functional language for adapting to category theory. The monad is a first-class construction. By that I mean it's in the language as an inherent part of the furniture that's built in. And so you have if you use the language, all the features are there. You don't have to run any library on top of it. Why is it called Haskell? Well, this Currying, Mr. Curry, if you like, his Christian name, first name, was Haskell. And so it's a credit really to Haskell B. Curry, and he was the one, of course, coming to the start of the talk, who transformed functions through currying in the lambda calculus.
What did the B stand for?
I don't know. You summoned. I thought you might ask somebody without something like that. I don't know. I don't even know what nationality is, I must say.
Facetious, sorry.
And even more surprisingly, the monad has actually been gaining some traction in commercial circles, because I mentioned most of these transaction systems are clapped out that they have at the moment, and the legacy systems, nobody really knows how they work underneath. And so Bitcoin came along with a blockchain transaction system which was based on the monad in Haskell. And at the time, people thought that Bitcoin were never a pretty out of line lot, you know. It doesn't. But I think the last 2 days ago, JP Morgan announced that they were going to be using the blockchain transaction system. And another bank as well. So in fact, this transaction system, well, when Mike and I were sort of theorising about it in a very naive way in 2010, now seems to be becoming the choice of a lot of big banks. The reason quoted is it's a simple and clean technique. That's I think that's quite amazing.
Just to comment, the World Bank or the IMF, the huge vision is that by 2025 we will be only on digital currency. They want to abolish all the dollars, the rands, the pounds.
So the Bitcoin techniques, yes, yes, yeah.
It's in one of the, I think it was 2010, it was in the,
to get rid of the cash.
The big view paper.
Okay. Right, so let's have a look at the monad, co-monad overview. Functionality. Yeah, a monad, t cubed, if t is a functor, then t cubed means you do it 3 times. T squared means you do the functor twice, and t once, it's multiplication. So in effect, you are looking back there from doing the cycle 3 times, doing it twice, doing it once. So that's one aspect the monad has. It has this ability to look back from the execution of the functor. So it's 3 cycles of t looking back. The co-monad, that's a dual of the monad. We always have co's, of course, in category theory. That goes the other way, from s to s squared to s cubed. So s cubed would be doing a functor 3 times. That's the basic idea. 3 cycles of s looking forward. You might think that the looking forward would be intuitively the most useful, but you're wrong, because in category theory we like to look back. And I suppose you could argue you need to get the results and look back. But so that's and the objects of this monad is an endofunctor on a category X. Endofunctor sounds a bit of a heavy concept. It's not. It means that for the functor, the starting point and the finishing point are the same. So it's the same category. Not quite the same category, don't like the word same. The finishing point and the starting point are identical. Yeah. So that's the overview of it. The monad is a 4-cell. I've just put this in as in tuple notation. The order does matter. So you've got 1, 2, 3, 4. 1 is a category X. 2 is an endofunctor, Tx to x. So endofunctor, x is the source category, and x is the target category. Functor the same, source and target. And then we have the normal, with 3 as the unit of adjunction, eta, 1x to t, change looking forward. And then we have 4 is the multiplication, that's how it links to the monoid, mu, t times t to t, change looking back. So a monad, if we translate those 1, 2, 3, 4, is therefore x, t, eta, and mu. That's the basic idea. So it's quite simple to define a monad. Yeah, this is where you get these things in science. Some people call this monad a triple, but it's not obvious why it's a triple at the moment anyway. But this resulted in a real bust-up between McLean, who didn't like the word triple, and Barr and Wells, who had a book with triples in the title, and so they rather committed themselves to using triple. So, but how we reduce it to a triple is that really we don't need to specify the category, because the category is included in the functor. T operates on X, Tx if you like. So we don't need to put the category in. Now, monad works over 3 levels for defining the rules and things like that. You can easily run the functor more times if you want, but 3 times is the norm. And this, of course, fits in with Peter Boland's, isn't it? 3-dimensionality. Yes, 3 levels seems to be enough for the world to tick over on very nicely. That's true. So the laws we're going to see involve T, endofunctor performed once, T squared performed twice, and T cubed performed 3 times. So that matches our transaction approach outlined earlier, the earlier one we had with GF performed 3 times. And then the dual of the monad, the comonad, which we don't actually use much later, that's category X, endofunctor SX to X. 3 is the co-unit of the junction, change looking back, and delta we introduce, S to S times S, is a change looking forward, and that is co-multiplication in the language they use. So a comonad ends up as S epsilon delta. So there's a co, obviously, to this one. It might be useful. It's, I think it's, we ought to include it in the definitions. Right, so the laws for the monad, this is where, again, I feel I have to put them in, but they really don't seem to add a lot to the application. They seem to be, so we've got the associative law and the unit law categories, right, these. So the associative law, you can see that these 2 arrows, this is T cubed, T squared, T. So we've got a commuting diagram going back. All this says is that if mu t is, you get the same result as if you apply mu t. Mu tu gives the same result as mu t, standard associativity. So, and it will be the same on the comonad side, that S delta delta is the same as delta S delta. So they don't add a lot to the application, but I think what the pure mathematicians are worried about is you doing something weird and stretching their work, and then you are falling foul of the rules, and it is a safeguard there. So I'm not really that critical. Right. And then this one is full of identities and equals. Left and right unitary laws. We have eta t there. Eta is strictly 1 to t, but you add the t there to bring it up to t squared. That's saying that e to t, you get the same result as if you do t eta. So if those don't work, then you're obviously in trouble for the sort of system you're using. Right, well, this is the most important thing of the lot, I think. It's an endofunctor, so you could argue, how does it handle the junction F and G? Well, that's because the starting category and the finishing category have to be the same. So here, we start off with X, go over to Y, and then we go Y to X. So if we run this adjunction, FG, then we actually are back at the start and the finish the same. So an adjunction is an endofunctor. So that means that we can use adjunctions in a monad. Without that, it would defeat our purpose completely. So we can take this this functor for which we're going to repeat several times, and we can use the adjunction. So GF is an endofunctor, as category X is both source and target. T is GF for monad, and S is FG for comonad. So this is looking a lot more promising with this as a structure. Free cell descriptors for the joints. Yes, so we can write the free cell monad T eta U. If you're going to write it now for an adjunction, then we write that GF, that's the functor, which we're running 3 times, GF. Eta is the unit of adjunction, and mu, we actually include epsilon here, G epsilon F, and we're very fond of doing this in category theory. We need to go up a level because the multiplication is looking back from T squared to T. So they just in the books, they say we drop an F in behind and a G in front, and that's a bit of housekeeping in effect. But that means our monad, for doing a lot of what we want to do, that's it there. So, and there's a free cell comonad, which would be Fg epsilon and F eta G. So you can see it's similar logic to that one, but it's reversed. That's the basic idea. So that means that we can use the monad for what we want to do. Monad is often simply addressed by its endofunctor. This is common, isn't it, everywhere in the world? So T eta mu is called the monad T. So we don't have to write out the whole monad all the time. And similarly, for the comonad, S epsilon delta is called the comonad S. It's a synecdoche, we're just calling it by a convenient handle, if you like. Right, so how do we operate on a topos? Well, the operation is very simple. If we're not going to do anything clever, we just we're now calling the topos E, and it's just T E to E. So the type isn't changed. We're going up. This is where again you get into an intension extension problem. Because obviously if you have a banking transaction, the E will have changed at the extensional level, won't it? This is something I'm not going to solve today, but it is, again, comes back. But the data type, the type at the intensional level, is obviously the same input and output. But in effect, I'm not sure how you would specify all the extra information you would need for the... I mean, obviously we're back, the E is really those pasted pullbacks that we had on the earlier slides, nothing, so that sort of thing would be the topos. And I mentioned, well, I should have mentioned there, you've got the intention, is that the intention or the extension you're looking at? And what you could say, I think if we rework it with the intention extension, then I think we are going to have to formally specify the intention and extension for all the stages. Like for the, you'd have to define the values, and then you'd have to specify the definition. And
no, I just got lost with where, because there was a definition that was really important.
Do you want me to go back?
Yeah, so that's, so, I mean, you're saying now it's got to, something's got to be looked at more. Like somewhere it was really important that the input and output were the same.
This really is intentional. It's at the intention level that we do, which is always very clean and simple. Yes, and simple, and very much easier to handle. And I say we have handled the extension before in work, but that's been a bit fragmented. I don't think it's actually been. So I think that is the advantage of giving a talk like this is that you realise that when you bring it all together, that there is a theme that needs to be addressed, and that theme I think is the intention extension, basically. So it actually, the operation is simple. Well, you're not changing the type. So, we are going to change the type in a bit, just to make it, just to make it a bit more complicated. Input and output types. Yes, I got it there, something about the extension will vary, but the intention remains the same. Closure is achieved as the type is preserved. Yes, so you've still got the... Yes, so that's very important. This closure is an extremely important aim of the work, because without closure, you're not getting anywhere. You're just getting values to print out on paper and things like that. You've got to get a topos out of it. Again, that's the basic idea. So this seems to be a very good match with what we want. This the use of the topos and the monad as it stands. We can do some other things though, and just to show, there really is quite a lot you can do with this to make things very much more capable. You can change the definition, and this is a more fundamental change to the operand, the X or E, and you can produce a new consistent state with what's called the T algebra. Now, the T algebra, the T algebra is a class of algebras defined for the monad.
What definition are you changing? Sorry?
I'm going to change at the moment we've got this adjointness F and G, and we have the topos E, but represented as a category X. But you can actually, with the T algebras, you can actually change the monad. So,
I'm just trying to get used to this one.
basically what mathematicians get up to. But you can see the average mathematician is going to be very bored with T, E to E. It's not very much of a challenge. It could be absolutely vital for people out in the information systems world, but it's not going to get them many more kudos. So. And it could be useful, this. So T algebras manipulate the category X when defined within a monad T. And some of this work's quite early. This was developed in work by Eilenberg and Moore in 1965. So let's have a look at this. Yeah, so category X, not necessarily a topos. In the monad, I've varied I've got all the four things there. Yes, you can actually, X is your old category, XT is your new category, and then you can define a new adjunction which maintains the relationship between this category X and that category XT. So you redefine the adjunction to restore the balance, if you like. So that's obviously very powerful. I'm not too sure what you'd use that for, but like a lot of things you find in maths, it may well come up as being very useful at some stage. You wouldn't certainly. So what I think I'm saying is that we are underusing the monad as it stands. I'm looking now at a few features that combining the monad with the topos is very rewarding for information systems, but probably quite a boring use of the technique, because I think there's a lot more to it. It's been very well developed. So for a topos, that's equivalent to a change to ET. So you go from that's your new topos, and that's your new adjunction. So that's potentially very useful, although we haven't got an application for it yet. But I suppose, if you changing any system, that would be relevant. As you know, if you change an information system, that is an enormous upheaval, keeping everything consistent. If you could actually do it as simply as that, or with that sort of basis, okay, right, that will be fine. And, yeah, so Yes, so the T algebra, I could go into a bit more detail on this. I think I'll try and go a bit faster though, just to finish them. T algebra is XH, where X is an object in X, and H, TX, that's the structure map of the algebra. And I've got two diagrams that commute, which I won't go into any further, and I'd rather leave a bit more time for questions. There are one or two other interesting things. Could deal with Beck's theorem first. When I said that this change, x to xt, now it's been developed to the extent that Beck's has a theorem which provides the rules on which the categorical transformations in T algebra are valid. So you can't change x to any xt, but if you look at Beck's theorem, that will tell you which ones you can change to. And in fact, it's sometimes called PTT, precise triplability theorem. So that means, is it triplability, meaning is it monadable? Triplability is making it monad. So this is actually being developed quite well. I think it could be useful for database change in design of information systems. If it works, all looks very abstract. The other important thing here is Kleisli. Category of a monad, because he's been responsible for this, in effect, for this work on blockchain and Haskell and the monad being possible. Because when people look at McLean's definition of a monad, which we've been dealing with, they said this is very difficult to fit into Haskell. But Kleisli, quite a while ago, he transforms a monad into a different form, and it fits much more easily with functional languages. So both those names are important. And we've also got Cartesian monads, which seem very interesting. We haven't explored these yet. If the underlying categories are pullbacks, which they are in our case, Topos doesn't have to be pullbacks, but ours are pullbacks. T preserves pullbacks, U and eta are Cartesian, and the monad is Cartesian. I think that would facilitate its use where a Cartesian type is expected. So, on these last few slides, I'm really showing that the potential for this hasn't been exhausted by any means. We're really using a fraction of the maths that has been developed in this area. So it is promising from that point of view. The other amazing thing about pure mathematicians is that they often, although they've got no experience of the information system world, some of the work they do is amazingly relevant. It's, although they're in the pure world, and must be to do with the way their minds work. Right, so I think we're finished with this one. So I think the Topos is pretty well established now as our data type of choice. And now we can handle elaborate structures. We're making progress with the sub-object classifier. That seems, and normalization has been dismissed. I think that's looking pretty set. The monad is where we're currently exploring what's going on. And I think it shows great potential for processing the Topos and for transforming the Topos. And I think if I was to be fair, after finishing my talk, I would say, but intention extension needs some attention in some of the area. They always say when you're giving a talk, you realise the problem for the next talk.
Was it supposed to have rhyme?
Sorry?
Was it supposed to have rhyme?
Yes. Oh, yeah. Yeah. Good. That's right. Yeah. So I think that's it.
Okay, that's good.
About 5 minutes for questions.
A very general question, is that in order? As I hear you talk about this, you're talking about processes which are mediated by some sort of computation system, and you gave examples starting from things that are all in a database through to a bank transaction which has got a little completable operation in a rather simple form, and you spoke about a bit further out than that. But in the end, you spoke of the blockchain. That's got asynchronous operations onto multiple databases, I believe, and I guess some of them can be missing, and you get into the feeling of process control with that sort of thing. Does this all apply to process control? Would it be applicable, say, to a part of the operation of an airport or something like that, where you've got scheduling and command operating?
You don't make that one transaction, because the transaction has to be atomic, and so you have to judge the size of a transaction. It's manageable. You can't have too much in one transaction. A process in an airport, though, might involve 10 or 20 transactions.
Well, right. Well, is there a way of cascading them so that you can, you can have local denials and things which cause that?
You've got to be careful there, though, because if you cascade them, and then the transaction at the bottom fails, strictly that should cascade back up again. You know,
it would have to.
Yes.
And
so you could end up with a
real-time. A command is conditional upon the circumstances that it finds.
You could have a real-time problem. That's all I'm saying. If you're using it for situations where real-time is important, then I think that you have to have a manual override.
That's right. There are lots of systems around this, aren't there? Even the truck dispatch system as well.
But if it's things happening in a fraction of a second or something,
well, it's a logical problem.
Yes, so you could cascade and build complex structures.
Oh, can I ask one more, Can I just finish? I noticed that Isham in Imperial College is doing a lot of this on physics, in fact.
Yeah.
Just 2 or 3 words on how you link in that sort of theoretical thing rather than the practical things which we were talking about.
In theoretical physics?
Yeah, how does this apply?
Well, I mean, in theoretical physics, the equivalent to here is obviously what I'm dealing with objects of data. They would be particle objects. So,
quantitative ones or pieces of theory?
Yes, there's no reason why you shouldn't feed those in as well.
And are you reporting on the Newcastle research work, or are you reporting on progress generally in cadmium theory?
It's specific. Well, it's specifically on the progress that Mike and I are making.
Okay.
Yeah.
And your reference to the bank or JP Morgan or whatever, are they doing it for real, or are they just putting around trying to see if it works?
Well, I don't know, depending on it yet, but no, it's for real. I think if you look up blockchain on Google, you Google it, there's something happened in the last 2 days, quite a major plan.
More than a number of banks who are investigating blockchain.
I think that's the key word.
No, but I think they're committed to it, aren't they? It's the only way they can get it to work in the digital.
It's basically, as I commented, during the talk, I think it was the ANPA, they had a working paper of 2010 in which they want all the currencies into a digital currency by 2029, which might be quite an interesting thing, what's happening to gold there, because people who know
no, I think it's way beyond what you might call interesting research.
It's backed up by the fact that the legacy systems have got to be solved because the people who design
They won't work in a digital money age.
Okay.
No.
It doesn't follow that has to be a Topos method, does it? Is that, are they somehow one-for-one, blockchain and Topos method?
What, from the to the blockchain?
I realise it. The blockchain is just a structure in its own right, I guess, isn't it?
Yes, it's ideally suited to they're using a distributed database and
the Topos method will be a way of rationalising that.
Yes. Yeah. But when you looked at all the problems involved with handling a transaction, the Monadic does actually simplify things. Makes it
believe
easy.
that.
Yeah. But there's not a lot to match, you could argue. The previous systems are very messy and complicated.
Give Nick another.